Hi there. This is the second video in this series on Fourier series. In the last video, we looked at periodic functions, what they are, how they are described, and we looked at the amplitude and the period of these periodic functions. And we saw that we write Fourier series primarily for periodic functions. So this video is going to focus on integrals of periodic functions. Specifically, we're going to write integrals for sine and cos, and they're going to contain integers m and n. And we're going to write these integrals over a single period. And what we have chosen as the boundaries is minus pi and pi. So the question is, why are we going to do this? Well, we need to do this because we get some important results that we need to use when we actually write out the Fourier series for different functions. So the first integral that we're going to look at is just the integral from minus pi to pi of dx. That's the constant. So if we integrate a constant, we'll just get x. And if we integrate from minus pi to pi, all we're just going to get is 2 pi. The second integral that we want to look at is the integral from minus pi to pi of sine nx dx. So you would remember that we just said we're going to look at all these integrals and they're going to contain these integers m and n. So these integers are quite important and we will see them in the upcoming videos, what role they play. So if we integrate this integral, it's fairly straightforward. The integral of sine is minus cos nx divided by n, and then integrating from minus pi to pi. So if we do that, we just substitute pi in. What we get is minus cos n pi divided by n plus, well, minus and minus, cos of minus n pi over n. And we would remember from our trig identities that cos of minus x is simply just equal to cos x. So once we substitute that identity in, what we get is minus cos n pi divided by n plus cos of n pi. Remember that this just becomes cos of n pi. So a minus and a plus just gives us 0. So that is the answer here. So the third integral that we're going to look at is simply cos. So we have integral from minus pi to pi of cos nx dx. So this is the third one. And that's just equal to the integral of cos is just sine. So we have sine nx divided by n. And we're integrating from minus pi to pi. So when we substitute in pi, we get sine of n pi over n minus sine of minus n pi over n. And sine of pi is just equal to 0. So we have 0 here and we have 0 here. So the fourth integral that we want to look at is where we integrate from minus pi to pi of cos mx times cos of nx. So for this specific integral that we're looking at now, what we will say is that m is equal to n. So this is important. So if m is equal to n, then what this integral becomes is the integral from minus pi to pi of, we'll just replace m with n. So what we get is cos squared nx dx. So if we want to evaluate this integral, then we need to use an identity. And that identity is that cos of 2a is equal to 2 cos squared x minus 1. So we just solve for cos squared here. So if we do that, we get that cos squared a is equal to half cos 2a plus a half. Take the 1 to the other side. So now we can substitute that in. And when we do that, what we get is the integral from minus pi to pi of a half cos 2nx, that's what the 2 is here, plus a half. So this is very straightforward to integrate. So what we'll do is just bring in the half to the front. So integral of cos is sine. So we have sine 2nx, and we will divide by n. 2n, sorry. We just integrate 1, and that gives us x, integrating from minus pi to pi. So once we substitute in pi, we get half into sine of 2n pi divided by 2n plus pi. Then minus, substitute in minus pi here, sine of minus 2n pi divided by 2n and minus pi. So remember, it's going to be minus here, and so we have minus pi. So this just becomes plus pi, basically. So sine of 2 pi is 0, so that term becomes 0. This term is also 0. Sine of minus 2 pi is also 0. So then we have pi plus pi gives us 2 pi. Then 2 pi multiplied by a half just gives us pi. So what we have is that if we integrate cos mx times cos nx, where m is equal to n, what this gives us is pi. So the fifth integral that we'll be considering is the integral from minus pi to pi of sine mx times sine nx. So we'll also state here that m is equal to n. This is for a very specific case where these two constants are the same. So if that's the case, what we get is the integral of minus pi to pi of sine squared nx dx. So we evaluate this integral in the same way that we had done the last one. So what we need is the identity, trig identity, that cos 2a is equal to 1 minus 2 sine squared a. Solving for sine squared a, what we get is sine squared a is equal to a half plus half cos 2a. So putting this into the integral, what we get is the integral from minus pi to pi of a half plus half cos 2nx. So we integrate this in the same manner as we had done the last one. If we do that, integral of half is just half x. Integral of cos is sine. So we have sine 2nx divided by 4n. We have to divide by 2n here, and we multiply by this 2 here, so that gives us 4n. And we integrate from minus pi to pi. Substituting in those boundaries, we get half pi plus sine of 2n pi divided by 4n minus half into minus pi minus sine minus 2n pi, so that's a minus here, that's minus 2n pi divided by 4n. As was the case previously, sine of 2 pi is 0. So we have half pi plus half pi, which is just pi. Okay, so we can proceed. So the sixth integral that we're looking at is integral from minus pi to pi of cos mx times cos nx dx. We had done this just now, but what we had said was m was equal to n. So now we are considering the case where m is not equal to n. So how do we evaluate this integral? So we need another identity, another trig identity, and that is 2 cos A cos B is equal to cos of A plus B plus cos of A minus B. And of course, we divide everything by 2. We have a half here and a half here. So putting that in, what we get is a half integral. Putting these terms inside, we get cos A plus B, so it's cos mx plus nx. So we'll just take out the x as a common factor. Okay, so we've taken out x as a common factor. We'll just write it in front. So it's cos m plus n x. So remember, this x is multiplied by what is inside this bracket. It's not being multiplied by cos. And then also in the same way, we have cos of m minus n x. All this integrated with respect to dx. So this is a straightforward integral to evaluate. What we get is a half. Integral of cos is sine. So we have sine m plus n, and we have to divide by m plus n. And the same is true of the other term. So we have sine m minus n divided by m minus n. Integrated from minus pi to pi. Substituting in pi and minus pi, we get a half into sine m plus n pi over m plus n, then plus sine of m minus n pi divided by m minus n. And it's essentially the same thing, but we'll just replace pi with minus pi. Okay, the first time we substitute minus pi, we get sine m plus n divided by m plus n minus pi, and the last term is also minus sine m minus n divided by m minus n and multiplied by minus pi. So all this is going to give us 0, right? Because sine of pi is 0 and sine of minus pi is equal to 0. So this entire thing is 0. So the seventh integral that we will look at is the integral minus pi to pi of sine mx times sine nx, and where we had previously considered m to be equal to n, we will now say that they are not equal. So if they're not equal, we need to use our trig identities once more, and the one that we shall use is that 2 sine A sine B is equal to cos of A minus B minus cos of A plus B. And of course, we can divide both sides by half. So substituting that in, what we get is the integral of half, you can write the half in front, cos of A minus B. So in the same way, it'll be cos of mx plus nx. So we'll take the x out as common factor. So what we have is cos m minus n x minus cos of m plus n x. And all this is integrated with respect to dx. So performing this integration, what we get is a half into cos, integral of cos is sine. So we have sine of m minus n divided by m minus n, and then minus integral of cos is sine once more. So we have m plus n divided by m plus n. And what we'll need to do, as was done previously, is substitute in pi and minus pi. So fairly straightforward to do. We get a half into sine of m minus n pi over m minus n minus sine of m plus n pi divided by m plus n. And now we substitute in minus pi. So, okay, so the next term would be negative sine m minus n minus pi divided by m minus n, and the last term is plus. A minus and a minus will give you a plus, so plus sine of m plus n minus pi divided by m plus n. And this entire thing is being integrated, sorry, it's already been substituted. So once more, sine of pi is equal to 0. So all of these terms become 0. Sine of minus pi is also 0. Okay, so the 8th integral that we're going to consider is the integral from minus pi to pi of cos mx times sine of mx. For this one, we need the identity that 2 cos A sine B is equal to sine of A plus B minus sine A minus B. And of course, we divide both sides by half. So substituting that into the integral, what we get is a half times the integral from minus pi to pi. And we have sine of m plus n x minus sine of m minus n x. So performing this integration, what we get is a half into minus cos m plus n x divided by m plus n plus integral of minus sine is cos, that's why we write a plus here. So we have cos of m minus n divided by m minus n. This is integrated from minus pi to pi. So substituting in pi, what we get is minus cos m plus n pi divided by m plus n plus cos of m minus n pi divided by m minus n. Then a minus and a minus gives us a plus. The next term is plus cos of m plus n times minus pi divided by m plus n. And lastly, minus cos m minus n minus pi divided by m minus n. So we remember our previous identity that cos of minus x is just cos x. So if you look at that term and that term, you'll see that the only difference between them is we have minus pi here, and with this identity we can see that they are the same. So that term is going to cancel out for that one, and it's the same for this one. So that term, second term, will cancel with the fourth term. So this also gives us 0. So the final integral that we're going to look at, that's number 9. So the last integral that we're looking at is the integral minus pi to pi of cos mx times sine mx. For this one, we need the identity that sine 2a is equal to 2 sine a times cos a. Okay, and of course we'll divide both sides by 2. So once we substitute this into the integral, what we get is a half, and the integral of sine of 2a, so in this case it's 2mx. So this is fairly straightforward. So this is half, integral of sine is minus cos. So we have minus cos 2mx divided by 2m. So once we substitute in pi and minus pi, what we get is half into minus cos 2m pi then plus, because the minus and minus gives us a plus. So it's plus cos of minus 2m pi. So once again, we just remember that cos of minus x is just cos x. So it means that this term is essentially the same as that term. So they just cancel each other, minus and plus. So this term also gives us 0. So we've looked at 9 integrals involving various combinations of cos and sine and different integers m and n and all of these things. So what was the point of all of this? Why did we do all of these? Or how are these integrals going to help us in any way? So you would remember from the previous video, we had written what the Fourier series actually looked like. The Fourier series for any function, f of x, is simply equal to a naught over 2 plus the sum of some variable n, which starts from 1, goes away all the way to infinity of a to the power an cos nx plus bn sine nx. So how these integrals are going to help us is to find the values of an and bn. So these things are called Fourier constants. So that is going to be the subject of the next video. We will use these results, these integrals that we have just written down now, and use them to find these coefficients an and bn, these Fourier constants.